Hey everybody, in this video we're going to look at a series. A series is when you are adding together an entire sequence of numbers. So for this particular series, we've got our terms that are going 2, 4, 6, 8, so on, all the way up to 96, 98, 100. Now we want to know what the sum of all of this stuff is. What happens, what value do we get when we add all of this up? Well, we could go through the process of adding each one of those and coming up with all of the terms in between there, in between 6 and 96, and add each one of those up and spend a lot of time doing that. Or we can see if there's some kind of recognizable pattern to help us with this. Now there was a mathematician, Carl Friedrich Gauss, who in his teenage years, maybe even a little bit younger than a teenage years, he discovered a pattern when you have a series of numbers, that if you take the series of numbers and you reverse them, so we do 100 plus 98 plus 96 and so on, if you reverse these and add your original series to this reversed series of numbers, you'll see a pattern emerge. So what he found was that when he added the first two, in this case it turns out to be 102, that then when he added the second pairs together, which is the second term and the second to last term, he also got the same number, and the third term and the third to last term also got the same number, and so on. And this worked all the way down the line as he added all these different values together. So how can we use this to determine what the overall sum is going from 2 to 100, increasing by a value of 2, right? 2, 4, 6. Well, first let's look at the way that the terms lay out. So if we call this term 1, and this is term 2, term 3, and so on, that means our last term is going to be term 50, right? Because we know if we're counting by 2s and we're going to 100, that's going to be obviously be half of 100, so we got term 50. Obviously that also means then, if you were going backwards, that this is going to be term 49 and term 48 and so on, working back towards the middle as well. Now we're going to use these ideas to help us determine how many 102s we have. So if we add all of these things across, we're going to have 50 102s because we've got 50 terms. So if we multiply our 102 by 50, we get this value of 5,100. Okay? But our goal was to add up 2 through 100, not 2 plus 100, 4 plus 98, 6 plus 96, all the way through. So what we have to realize is that we actually had two sets of our terms here. So when we're looking for our final value, we have to divide it by 2, and we end up with 2,550. Now you're probably thinking to yourself, great, what's that do for me? Well, nothing as it stands right now other than seeing a really cool pattern. But what we're going to do now is we're going to see if we can find out or determine some kind of general formula for this that will work for any arithmetic sequence. Now remember, these are arithmetic because they're being added together. Term 1, term 2, term 3. We're adding all of these values together, right? Or we're adding a common difference to each value. So if we go from term 1, term 2, term 3, and we go all the way up to the end, no matter how high we go, we can call that our nth term. So just like we did before when we had the 50th term, we knew the term before that was 1 less than n, was 49. So 1 less than n is going to be t to the n minus 1 power, or not power, to the t to the n minus 1. And the term before that is going to be t to the n minus 2. So we come up with this general pattern here, right? So we're seeing how this looks in general terms. Now, what do each of these things mean? Well, our term 1 is term 1. Our term 2 is going to be whatever term 1 is plus our common difference. Right? So in our first example, our common difference was 2. So we had 2 plus 2, we got to 4. Then we added again another 2, and we got to term 3. So here what we would do is we'd add another d, another common difference, and we've got t of 1 plus 2d, right? And we keep on doing that all the way up until we get to our nth term. And at that point, we're looking for a little bit of a pattern here. So if we have our nth term, then we can see here that we have marked in red that our second term we went to one common difference. Our third term we had 2 common differences. And it's going to work the same way as we go backwards. So to get from t of n down to the value of the terms prior to that, we're going to have to subtract our common difference. So we're going to have t of n minus 1d. And look at the example up above in the black numbers. We have 100, and then the term before that was 98. So we subtracted our common difference of 2 to get to 98. So that's exactly what we're doing in this green, t of n minus 1d. And if we went back 2 terms, so if we went back to the 48th term, we subtracted our common difference twice. So here we would have our t of n minus 2d, right? So that's another way to write this whole series using our common differences. And this will help now as we try and develop this general formula, because as we reverse this green line, we'll end up with t of n plus t of n minus 1d plus t of n minus 2d all the way up. And now again we're going to be working from the front. So now we've got t of 1 plus 2d, t of 1 plus 1d down to t of 1. Now if again, look, all these things match up. All we've done is reversed the order. That's the only thing we've done. Now we're going to add it like we did above. So we're going to add this whole thing. And our first pair is t of 1 plus t of n. Hopefully this is making sense. Our second term, or our second pair, when we add them up, well, if you notice, this 1d and negative 1d cancel out. And we're left with t of 1 plus t of n. And if we look at the third pair, the 2d and the negative 2d cancel out. And we're left with t of 1 plus t of n. And we can keep on doing that all the way through. Our 2d's cancel out again. And we just keep on going and going. And we get our t of 1 plus t of n all the way through the whole thing. All of the common differences cancel out. So how many of these t1 plus t of n do we have? Well, just like above, we've got 1, 2, 3, well, wait a minute, we go up to the nth term. So we've got n numbers of t of 1 plus t of n. So when we add all these things up, we've got n times t1 plus tn. But remember that we had two sets of the series. So we have to divide this thing by 2. And that gives us this nice general formula that we can use, which is we call it S of n for the summation of all the values up to n. So this S of n is equal to n over 2 plus, or times t of 1 plus t of n. And that is a good general formula that you can use for arithmetic series. And we use that based on any given information that we have. So you may have seen in another video when we talk about series, we can use that to find the sum of a bunch of numbers, or we can use this. And this will come in handy when we look at our next examples. So let's say we've got an arithmetic series or a sequence. Let's review what that formula looked like. That's u of 1 equals u of 1, or u of n equals u of 1 plus n minus 1d. In our arithmetic series, now, the one that we just did previously, is S of n is equal to n over 2 times u of 1 plus u of n. Now notice I jumped from t to u. That's okay, just as long as you're keeping the subscripts common. It doesn't matter what variable you use. So we've got these two values. So here's, we're going to look at an example, and our example is going to be, see if we can speed this up here. Our example will be calculate the sum of the first 15 terms of the series, 29 plus 21 plus 13, and so on. So, first thing we need to figure out when we're calculating this is what is the common difference. So as we go from 29 to 21, we're subtracting 8. As we go from 21 to 13, we're again subtracting 8. So we can say that our common difference is negative 8. We also know that our first term is 29. But what is our 15th term, our u of n? Well, we don't know what u of n is. As far as using our arithmetic series formula, we don't know what that u of n is. We know n is 15, so we could do 15 over 2. We know what u of 1 is because we know 29, but we don't know what that u of n is. Fortunately, if you look at the sequence for, equation above that, our u of n is listed right here. So we can plug in our u of n from the arithmetic sequence into the u of n in our arithmetic series. And we get this new formula. It's kind of like a composite function. We're going to plug one function into another. So we're going to get n over 2 of u of 1, or times u of 1 plus u of n. And u of n of the arithmetic sequence is u of 1 plus n minus 1 times d. As we simplify, we get our 2 u of 1's, and then we have our n minus 1 times d. So now when we start taking this into the given values that we have above, we can say the sum up to our 15th term is going to be 15 over 2 times 2 times 29, our first term, plus our n minus 1, which is going to be 15 minus 1 times d, which is negative 8. Now it's just a matter of doing some basic computations, and we get, what's this, 15 minus 1 is 14 times negative 8, negative 112. Do our division, 7.5, 58 plus negative 112, that's negative 54. Multiply it together and we get our negative 405. So the value of this, of having this series, the arithmetic series written out this way, and the arithmetic sequence written out this way, is, again, based on different unknowns or different givens. You can combine these things. You can use either one individually. If you have enough information, you can use the sigma notation if you know about that. So there's a lot of different ways that you can think about this. But this arithmetic sequence, this arithmetic series, and maybe even this combined function is really going to come in handy as you're working through arithmetic sequences and series. So hopefully this made sense. I talked a little fast, so if you need to go back, make sure you rewind and make sure you know where all of these things are coming from, how we're flipping the series back and forth, and coming to these conclusions. That's it for this one, and I will talk to you soon.